You see this? This was supposed to be a custom mounting bracket for the drill press. Now it looks like a plate of spaghetti that got into a fight with a heat gun.
I mean, it's modern art, Tiger. You could probably sell it for a few $100 in the right gallery. But for a mounting bracket? Yeah, that's a tragedy. What happened? Did the printer catch a cold?
Not the printer's fault. It was the operator, specifically the guy staring back at me in the mirror this morning. I tried to treat this 3D printer like a tiny automated woodworker. I designed the part like I was going to cut it out of a block of oak on the bandsaw. But plastic doesn't have grain, Alex, and it definitely doesn't like gravity when there's nothing underneath it.
So you forgot the golden rule, didn't you? Designing for the tool, not just the shape you want.
Exactly. It's called DFAM, Design for Additive Manufacturing. But I prefer to think of it as don't ask the machine to defy physics. I had 2 inches of plastic just floating in the breeze. No supports, just hope. And hope is a terrible structural material.
Hope sags at 200 degrees Celsius. I think a lot of people jump into 3D printing thinking it's a magic box where you put in a 3D model and out comes a product. But it's really more like building a house one brick at a time, except the bricks are liquid for a split second.
That's a great way to put it. When you're at the computer, you've got total freedom. You can draw a floating castle in CAD. But the printer is a blue-collar worker. It needs a floor to stand on. One of the biggest hurdles I see, and I tripped over it face first today, is bridging.
Bridges. That's when the nozzle has to travel between 2 points with nothing but air in between, right? Like a tiny plastic tightrope walker.
Exactly. If you're spanning a gap of maybe 5 millimeters, most modern printers can handle it. They just zip across, the plastic cools fast enough to stay mostly straight. But you try to span 2 inches, that plastic is going to droop like a wet noodle.
So if you're designing a part and you absolutely need that gap, you're either looking at adding support structures, which we all know are a pain to peel off, or you have to get clever with the geometry.
Right, and those supports, man, they leave scars. It's like trying to remove a stubborn sticker from a new frying pan, but with pliers and a hobby knife. You're always going to see where they touched. If I'm making something that needs to look slick, I'll actually split the part in 2, print them flat on the bed, and glue them together later. It feels like cheating, but in the shop, cheating is just another word for efficiency.
It's not cheating, it's strategy. But what about holes? I've noticed every time you print a hole for a bolt, you end up reaching for the drill bit anyway because the bolt won't fit. Why is the machine so bad at circles?
It's not that the machine is bad at circles, it's that it's too enthusiastic. Think about the nozzle like a tube of toothpaste. When it's drawing that circle, it's squishing the plastic down to make sure it sticks to the layer below. That squish moves the material outward. In a hole, outward means inward toward the center.
So the hole shrinks because the plastic has nowhere else to go.
You nailed it. It's a game of fractions. If you need a 10 millimeters hole and you draw a 10 millimeters hole, you're going to end up with a 9.8 millimeters hole and a lot of colorful language. My rule of thumb is to either bump the size up in the model by a hair, or, better yet, print it slightly small and let the drill press do the final sizing. Metal and plastic both respect a sharp bit more than a digital file.
You mentioned earlier that there are different flavors of these machines. We usually talk about FFF, the ones that use the spools of plastic string. But what about the resin ones, the SLA printers? Does the design change when you're dealing with a vat of goo?
Oh, big time. It's a totally different beast. FFF printers are building a skyscraper. SLA, stereolithography, is more like growing a crystal upside down. Since the part is being pulled out of a liquid, you don't worry as much about bridging, but you have to worry about suction cups.
Suction cups? Like it gets stuck to the bottom of the tank?
It's terrifying. If you print a hollow cup facing down as the printer pulls it up, it creates a vacuum. The machine is fighting to pull that part out of the resin, and if the suction is strong enough, it'll just rip the part right off the build plate. You have to design drain holes into the model so the liquid and air can escape. It's the kind of thing you only forget once because cleaning a resin tank after a failure is about as much fun as unstopping a sink with your bare hands.
So in the FDM world, we're fighting gravity. In the SLA world, we're fighting fluid dynamics. It sounds like you need a physics degree just to make a replacement knob for your dresser.
Well, I skipped the degree and went straight to the school of expensive mistakes. But there's a third one too, SLS, selective laser sintering. That's the high-end stuff where a laser shoots a bed of nylon powder.
And that's the holy grail, right? Because the powder itself acts as the support.
Precisely. You can print a gear inside a gear or a fully assembled chain and it just sits there in the powder bed like a fossil waiting to be brushed off. But even then, you've got to think about internal volumes. If you print a hollow sphere, you're going to have a ball full of trapped, expensive powder that you can't get out unless you put a hole in it.
Okay, so regardless of the tech, the common thread is stop thinking about the finished shape and start thinking about the path to get there. It's like planning a road trip, but focusing on the quality of the asphalt instead of just the destination.
That's a hell of a way to put it. You also have to consider the grain of the print. Even though it's plastic, FDM prints have layers. They're like a stack of Pringles. They're really strong if you're pushing down on them, but if you try to snap them along the seam, they'll pop right apart.
So you shouldn't print a long, thin peg standing vertically if it's going to take a sideways load. It'll just snap at one of the layer lines.
You've been paying attention. If I need a sturdy peg, I'll print it lying down on its side. The fibers of the plastic will run the length of the peg, making it 10 times tougher. It's the same logic I use when I'm picking out a piece of straight grain hickory for a hammer handle. You want the strength to follow the stress.
Is that why you were talking about generative design the other day? That sounds like something a computer does while you're out getting coffee.
It kind of is. You tell the computer where the bolts go and how much weight it needs to hold, and the AI grows the part. It only puts material exactly where the stress is. It ends up looking like something out of an alien's ribcage. You couldn't make these shapes with a mill or a lathe if you had 100 years, but a 3D printer doesn't care how weird a shape is.
It's weirdly beautiful, but I bet it's a nightmare to clean up if the print fails.
Let's just say I've spent more hours with a pair of tweezers and a magnifying glass than I care to admit, picking plastic bits out of those nooks and crannies. But when it works, when you hold a part that's half the weight of the original but twice as strong, that's the magic.
We've talked a lot about the technical headaches, but what about the why? For a maker like you, who loves traditional wood and metal, where does 3D printing actually earn its keep in the shop?
It's the connective tissue. If I'm building a table and I need a weird custom jig to hold a piece at a 17.5-degree angle while I glue it, I'm not going to spend 4 hours machining that out of aluminum. I'll sketch it up, hit print, and go have dinner. By morning, the tool is sitting there waiting for me. It's not about replacing the craftsmanship. It's about making the craftsmanship less of a chore.
So it's the ultimate shop assistant. Doesn't talk back, doesn't drink your beer, just works through the night.
Usually, unless it decides to make spaghetti art like this bracket here.
Well, before we wrap up and I watch you try to salvage that mess, what's the one nugget of wisdom for someone who just unboxed their first printer and is staring at a blank CAD screen?
Stop trying to be perfect on the first go. In the woodworking world, a mistake means you just turned an expensive piece of walnut into firewood. In 3D printing, a mistake costs you maybe 50 cents of plastic and a little bit of electricity. Fail fast. Print a tiny version of your design first to see if the holes fit and the bridges hold.
Test the waters before you dive into the deep end.
Exactly. The CAD software is a liar. It'll let you draw things that can't exist. The printer is the only thing that's going to tell you the truth. Listen to the machine, and eventually you'll start seeing the layers before they're even printed.
I think to a lot of people, that's the most intimidating part, the fear of the failed print. But you're saying the failure is actually the instruction manual.
It's the best teacher in the building. Every time a print curls off the bed or a thin wall collapses, it's just the plastic telling you, hey, I can't do that. Try it this way. Once you stop fighting the material and start working with its quirks, the magic box actually starts to feel like a tool.
Well, I'm going to go see if I can find a frame for your spaghetti bracket. I still think we can move it for at least $50 at the craft fair.
Deal. But you're handling the shipping. I don't want to be responsible for any more unintentional geometry.
Fair enough. Next time, let's talk about how you nearly set the shop on fire trying to dry your filament in your wife's toaster oven.
We said we wouldn't bring that up on the air, Alex.
See you next time in the Tiger Den. Main takeaway. Designing for 3D printing is about shifting your mindset from the final shape to the printing process itself. Success comes from respecting the limitations of the technology, like gravity's effect on bridges, the squish that shrinks vertical holes, and the directional strength of layer lines, to create parts that are not just possible, but optimized for the medium. Fail fast, prototype small, and treat every failed print as a lesson in physics.